All right, so okay, so what I'm gonna do today is could have done it differently, but anyway, I set up the homework for you, but that's basically what we're gonna do. So I'm basically gonna be explaining the homework, so it's easy, but I wanted you to do it, so I made it a homework. But if you went to the form, if you follow the link, there's a what? That's weird. Okay. So on here, there's a download to the file which contains the problem, and also there's a link to the form. So yeah. So if you type in the name and stuff, you should see the problem, which is something like this. But basically, that's what I'm going to explain now. So you should see a file like this. It has two sections. Section 1 has a bunch of these. It should say section 2. I think it will. But section 2 will contain something like this. And I hope to talk about both today. So I guess just a little bit about the trust. I'm really glad that, most of you guys seem to have got almost everything correct in the test, and I'm really glad that it's great. And I think that's actually kind of the power of the graphic methods. But I guess just to let you know, there are other methods for solving trust reactions. You can, I guess I might post the link, but there are other methods. One is called methods of joints, and you can probably, so you can do, so if you want to know, I'm not going to cover that in class of graphic methods, which is actually, you can use that to analyze the trust, but you can also use it to sort of design the trust to come up with the correct form and stuff. So section 1 is kind of a guideline or gateway, and then section 2 we are really going to kind of design the trust. So let's do the section 1 first, which, by the way, for those of you who came in later, that's basically the homework today. So I'm basically explaining half of the homework. So now, so the questions are like this. So internal forces in each member of the truss is shown on the right. If you turn on this layer solution, you should see this. This is basically what we had for these 6 panel trusses, right? So you see this truss, right? And the question is basically, so let's look at, so I'm asking you to redesign this truss so that the tension in the chord between zone 5 and G, which in this case right now it's 40 kPa, but we want to reduce the internal force of that member to 16, right? Everything else would stay the same. So the loads are going to be the same, therefore the reaction is going to be the same. So so how are we going to do that, right? It's probably the problem is, this tension was too much, and it's exceeding what's allowed for the particular member or something like that. So we've also learned already, right? Making the truss deeper decrease the internal forces a lot, right? So basically the depth of the truss directly correlates to the amount of tension at the bottom and compression at the top, because I guess if you remember, as you scale the truss geometry up and down, so as you scale the truss geometry up and down, what happened in correspondence to that was the force diagram scaled horizontally, bigger and smaller. So the deeper the truss gets, so if the truss elongates in y direction, then the diagram shrinks in this direction. So there's direct correlation to that. So this is actually pretty easy. So now what I was asking you is to reduce this tension to 16K. So we can pretty much directly, because none of the other condition is changing, we can pretty much directly manipulate the diagram first and then use that as a guide to determine the depth of this truss. So let me turn off this layer because I don't need them. But just to remember, 5G, that member was 40K, because if you do a dimension, let me see, let me use a different color. Because the internal force 5G was determined by lengths between G and 5 on the force diagram, right? So it was basically a length between here and here. And it's 400 inches currently, and that was 40K because we're using that. Let me copy this force scale, which is huge, so because we're using this force scale where 1 inch represents 100-pound force, right? So basically we need to manipulate the depths of this truss so that the distance between 5 and G is not 400, but it has to be 160, right? Because we want to change the 40K to 16K, so it has to be 40% of the size. Let me actually have two views to show the force diagram and form diagram. So let me go here and let me move this to the side so we can see both. Right, so we're basically trying to reduce that by 40%. So what we want is for this guy to shrink to 160. So what I would do is I would draw a circle starting from point G. I draw a circle with a radius 160, right? And then I would make an intersection between that horizontal line and the circle, just to make sure that's our target point. Right, so from here to here it's 160. So basically we want to make this into this, right? So all I'm gonna do is I'm gonna grab this whole thing and I'm gonna type in scale 1D. I'm gonna start from point G, and I know it's the point 5 that wants to move here, so I'm, as a first reference point, I'm gonna click on the point 5, and then just go horizontally and click on that intersection point that we made as a second reference point, so that we can make sure that the distance between 5 and G is 160. So that's basically, that's the force diagram that we want this truss to have. So now something is not working because it doesn't completely match the geometry of the truss, right? So the easiest guide to use is this diagonal line, and for example, this force 1, 2, force in member 1, 2 should be parallel to this. Sorry, the member between 1 and 2 should be parallel to this force that's shown here, which is 1, 2. So I'm gonna copy this to here. So basically this diagonal guy has to be at this angle, meaning that the truss needs to get deeper. And just want to make this line big enough so that it extends, right? So basically it means that the depths of the so depths of the truss, it's currently, how deep is it? It's here, 72 inches. And we need to increase the depth of the truss by however much. It needs to go over there. So it needs to get to 180 inch thick or deep. So these forces are not changing, so I'm just gonna grab them and move to the side for later. And I'm gonna grab this entire truss, right? And I need to do scale 1D and go from this to that intersection point. So now this diagonal member matches exactly what's in the force diagram. And the depth of the truss is 180, and the loading pattern is exactly the same, so I'm just gonna bring this back. So basically that's what's in the, if you click on the homework link, not this, but if you went to this form, and after you enter your name, so that's what I'm asking basically. So the depth of the truss after the redesign for Q1, which is, so I have Q1, Q2, Q3, Q4. So for Q1, the depth of the truss after the redesign is 180 inches. So I want you to enter and also round to the closest integer, the whole number. So I want you to enter 180. That should be the correct answer. I think I have everything correct. So I just want you to enter whole numbers for these four. That's basically the homework. But I've already solved one for you. But I think this is pretty profound, right? So with other method, you can, equally analyze these trusses. But I think the graphic method is the only method where, like, we were able to say, so now all of these are not correct, but we were able to say, I want to change this internal force in this member to a specific number, and we were able to manipulate the diagram and then dictate what form should the truss should have. So we have the ability of working backwards from force diagram to design the geometry of the truss. So I think that's kind of profound, and so this is kind of the intro to that. So this should be fairly quick. So I want you to actually, so now that we solved one, which is pretty easy, I want you to do question 2 and spend like, I don't know, 10 minutes, and then we'll solve it together. And you should already have the force diagram too, right? So try to do the same, manipulate the diagram to, so I guess what I'm asking for the second one is I'm asking the compression between zone 6 and what? G. No, that sounds wrong. 6 and G, that's a tension, right? Yeah, so sorry, I wrote it wrong. Okay, so the question, there's a minor mistake in here, so that the tension in the cord. So basically, I want to change the tension here to 13.5, right? That means 6G, currently 450, that wants to be 150. So that's how you should shrink the force diagram, and that's going to dictate what the truss will be. And I think, yeah. Yeah, so it's basically, so let's say this wants to be 150, right? So first I would do circle, that's a radius of 150, and intersect, make the point. It's scale 1D.
I'm sorry.
Yeah.
What's the radius of that circle?
Oh, sorry. So yes, so basically in the problem I'm asking to set the tension in this member that's between 6 and G, which is currently 45K, right? And applying this force scale, so force in 6G was determined by the length or distance between 6 and point G, right? It's currently reading it as 450. I'm asking this force to be changed to 13.5. Oh, so 150 was wrong, sorry. So it has to be 30% of that, so it's gonna be the radius of the circle. Basically, we want that distance to read as 135, because that's the equivalent of 13.5K. And then I would make an intersection between these two, right? That horizontal line and the circle that I drew from point G. And just to confirm, the distance between the point and point G is 135. So basically what I want to do is I want to scale this whole diagram so that the 6G is 135, right? So then what I'm going to do is I will select everything that I want to scale, and you type in scale 1D. That just lets you to scale things in one direction. So then I'm going to start from point G. First reference point is point 6. Second reference point is that point that I just created. So that is 135. So now this is going to make a really deep truss, because these, for example, this 1, 2, that diagonal member needs to be at this angle, right? So again, I'm just gonna extend this line to the vertical line so that it matches. I don't need all these internal forces because they're gonna be wrong anyways. These pink ones, these are external force, so we shouldn't scale those because those are not changing, but everything else here is gonna change so that in one direction, so that the angle matches that one. So I think the second one, the right answer would be 240. I hope I put the right answer. I think. I got it wrong because I wrote 15 over there, so I should change that to 240. Anyway, if you suspect the answer is wrong, let me know, because I make mistakes.
When you're scaling the truss, you do scale 1D as well?
Yeah. This is 240 then, yeah. Question 3 might be slightly tricky because now I'm asking force 1, 2 to be 15K. Currently 1, 2, that is 28. So it's just a little bit tricky where to draw that circle. So basically what I'm wanting to do is I want so let's say if you do a linear dimension, pick the fourth one, aligned dimension. This is question 3. If you measure between 2 and 1, currently it's like 279.51. I'm asking that to be 15K, so that should be 150. So what I will do is I'm gonna draw a circle from point G, radius 150, but don't take the intersection there, because what it's gonna do is basically what we are doing is we are trying to find the right spot so that when we do scale 1D, right, so you see that angle is changing, the line 2, 1, 2 wants to be touching that circle, right? So you see how the point 2 is moving horizontally. So what we want to do is to make a intersection point between horizontal line from point 2 and this circle. And then I'm just gonna turn the control points on for this dimension. And then I'm gonna grab this whole thing, scale 1D, and then it's 150. But if you try to, right, because everything is just changing in this direction, it's not moving in vertical direction. So that's basically what you want to do. So this one was a little bit tricky, but it was recorded, so it should be fine. Right, so I'll just do it once again. I'm gonna turn the control. Yeah.
How do you make the dimension go sideways?
Yeah. Okay. So go here and pick the fourth one, which is aligned dimension, or I guess you can also type dim aligned, and that way you can pick whatever point. And so I'm gonna turn the edit point on for this dimension. I'm gonna grab this whole thing and then scale 1D and grab the 2 and make sure that it snaps to that point. That way the resulting 1, 2 ends up being 150 inches. So this is, again, I'm gonna use that angle to guide the depth of the truss. So I guess that's the only slightly tricky part, but I think, you know, just the ability to tweak this and determine the geometry of the truss is pretty neat. So now that was just kind of a precursor. So now we're gonna go to a really kind of more actually design type thing. So if you move, I don't know if I labeled it as section 2, but this is basically what I want to look at, is what's on the right side. If you go to the 3D view, you would see a truss like this. So basically what we're doing is, I mean, this is, you could sort of think of it as a ceiling for a gymnasium or something like that, but you know, you would assume a roof like this, supported by a truss like that. So we are assuming the geometry of a truss to be roughly something like this, but we don't necessarily know the correct angles and all that kind of thing, right? So that's what we need to determine. So basically what I'm asking you is, I'm giving you a floor load by 25 pounds square feet, and we translate that to point load, and then we're gonna draw a diagram. So this is actually not a correct geometry, but given this point load, I'm asking the force, internal force at the top chord. So basically this one, this one, this one, this one, this one, this one. Like, we want all of these to be have the same internal force. The efficiency of that is, if you design it such that all of these have same internal force, you can basically use the same member size, right? Like, depending on what material and the cross section, right, you can calculate the stress, but the stress along this top chord is constant, so you're guaranteed to be able to use the same size all the way across. You know, otherwise you might have to have as you remember, the rectangle ones had, you know, bigger compression on the top chord in the middle, right? So you might have had to use a thicker member in the middle. But now, like, so we're gonna force the top chord to have same internal force all the way across, and then that's gonna determine the correct geometry for everything else. So that's what we're gonna do. But as a sort of just to kind of, I guess, I think we all covered this, like, you know, pound per square feet, which is the floor load. You translate that to, if you're looking at a beam or truss that's taking care of that part of the, right? So let me cover that first. So how to translate the floor load to point load, which isn't the meat of this discussion, but I guess just a refresher, right? So, so the problem is at the very left. So suppose you had a 80 feet, 960 inches by 60 feet roof or room, and your roof load was 25 pounds square feet. PSF, I don't really like that way of notations. I wrote it as pound force per feet square. Same exact thing. So you sketch an idea of a series of trusses 20 feet apart to carry the roof load, but you want to make the trusses visually interesting, and so it will be an exposed roof truss like this, and you want it to be nicer than maybe something like that. Anyway, so we know the roof load is 25 pounds per square feet, and the roof that we are supporting is 60 feet by 80 feet, and you have a 20 feet spacing between all of these guys. So if you remember this concept, tributary area, right? So that let me see, this whole thing 60 by 80, that whole rectangle, which is this yellow, that's the entire roof. But just looking at the way the trusses are spaced, I forgot to put the dimension strings, but they are 20 feet apart, right? So given that spacing, first you determine the tributary area, which is basically the area by basically how much of this roof slab each of these truss is carrying the load to, right? So if there are 4 of them, they have to be distributing the work. How to determine the tributary area? It's simply by determining the midpoint between the two truss. So you take the equal distance, that's the boundary. You take the equal distance to the next truss, that's the boundary. So basically these, for example, if you take that one hatch, that's the portion that's being taken care of by that one truss. Does that make sense? Or we covered this in structure 1 for me, and supposedly if you didn't do it with me, you've taken structure 1 somewhere. And like, is everyone familiar with the concept, more or less? Yes? Closed eyes means something else. So you're familiar, right? Right. So anyway, so just showing you graphically. So that would be the area that's taken care of by each of the truss. So I mean, it wasn't necessary, but I'm just showing you, like, this is roof load 25 pounds per foot per square feet. So that's a square feet. Each square is square feet, and each of these are 25 pound force. So because this one truss is taking care of that area, what you do is basically kind of squish that whole surface into a line, right? So that's a 25 pound square feet, but this 20 feet width is being taken care of by this truss. So what you do to convert that to a pound per linear feet, you basically take the thickness of or width of that slab that this truss is taking care of. So instead of 25 pound per foot, pound per square feet, you multiply that by 20, which is the width of that. Now it becomes a linearly uniformly distributed load of 500 pound per foot, right? So that's basically the uniform distributed load for each of these trusses, right? So each linear feet, which is right? If you take that much, that portion right there weighs 500 pounds. So that's gonna go on for the entire span. And it's very common when we are analyzing the truss to assume that in reality it's a distributed load, but when we calculate for the truss we would assume everything is a point load. So we're gonna distribute this 500 pound per foot into 1, 2, 3, 4, 5 separate point loads. So if you, and this whole truss is 60 feet long, right? So if you calculate the total load for this, each of this truss, it's 500 pound per feet times 60 feet, which is the length of this truss. So you have 30,000 pound for this entire truss, and we're dividing that equally by 5 so that it turns into like these 5 equal point loads. So each of these point loads are 6,000 pounds. Is that okay? Right? So went through really quickly, but because that's not the main thing that I want to talk about. So anyway, so we took that step to calculate the point load, so we can translate that calc into a diagram like this. We have a truss like this, and we have these point loads, 6,000 each and 1,500. Let me just do A, B, C, D, E, all the thing. Did I have that in there? Maybe I have that in there already. So let's look at this truss, and yeah, okay, so I drew them in there. So I'm assuming, right? So basically that's the truss. We more or less know the geometry of the truss. What we don't know is how deep these angles are correct or not. And what I'm asking with this question is, again, we want the top chord of our truss to have a constant force throughout the span. So we want A1, B3, C5, D6, E8, F10, all of that to be constant force. And yeah, again, remember, if you know, in the previous truss, the 6-panel truss, the forces in the top chord varied, reflecting what happens with the bending moment throughout the span. Right, so it gets bigger and bigger as you get to the middle. So the challenge now is to find the right form so that the force in the top chord is constant. And so we need to make an assumption what that internal force would be. So we just decide to make this truss, yeah, you know, we use steel, and we choose to have a constant force of 20,000 pound force. I want to say LBF, but that's okay. Along the top chord, so that it's not yielding. Anyway, so that's the assumption, and we're using this force scale, right? And let me divide the view. So we have this. So that's the force scale we are using, and then I'm gonna have a top view here too. And then I'll show this diagram. So here what I'm showing is, let me just redo this whole thing, which is, so I'm going to start the force diagram now, right? So what I'm going to do is same as always, right? You have 1, 2, 3, 4, 5 equal applied forces, and I've already calculated the reactions because it's symmetrical and simple. So the reactions are 15,000 pounds. So what I'm gonna do is, yeah, so I'll copy these to the right, 1, 2, 3, 4, 5, and then you have the reaction, right? So you should end up, well, let me redraw this whole thing so that we know, but we start from point A, right? The force diagram, it should be an uppercase. So it's gonna start from point A, downward force, right? And the next one is B, right? I'm just gonna change that to upper scale, capital letter. Next one, it's the same, BC, CD, DE, 1, 2, 3, 4, 5, EF. So it should read A, B, C, D, E, and F. And they should be all capital letters. Same exact process, and reaction here goes up from point F, and the midpoint is point G right there. Okay, so that's point G, G, and then the second reaction is gonna start from point G and ends at point A. So that's super straightforward, right? So another thing we know, so there are a whole bunch of unknowns. We don't know the angle of this guy. None of these angles actually we don't know. But one thing we know is all of these horizontal one, I think I said 20,000, right? So we know all of that to be 20,000 pounds. So for example, if you analyze per this point, right, we have this member which is A1, and we know that to be horizontal. This one we don't know the angle, but the top one we know that it's horizontal. And we even know the force in that thing, and so let's just say it's 20,000 pounds. Technically we don't know if it's compression or tension, but we pretty much know it's compression. But in this case it doesn't really matter that much. But so one thing we know is the this cord is horizontal, and it has 20,000 pound force. And so basically from A to point 1 it should be a horizontal line, right? And it should have a length that signifies 20,000 pound. So in this case, because we're using 1 inch equal 100, and what is it? The 60 inches, 60,000. So we want this to be 200 inches. So we just need to, what we need to do is we just need to draw a line that is 200 inches long to the left, and that's where the point 1 should be. That makes sense so far? Everyone awake? Okay, so now actually there's something profound, because this we knew, this we didn't know. 1G, right? It's like G is right here. So this diagonal, maybe let me change the color to red or something temporarily. So this red guy between 1 and G, that angle we didn't know now, but now we should know, because we can connect the point 1 and point G on the force diagram, and that should absolutely correspond to the geometry of the truss. So that's actually right there. So instead of this red line, it should have been drawn at this angle, right? So let me actually turn all of these, because these were just assumptions. Let me turn these into a, I don't know, let's just lock it so that it turns gray, and it's kind of obvious that it's not correct. But now we are actually able to determine G1 from this, right? So that's kind of nice. Other things we know for sure is all of these horizontal one has the same distance. So B3 is, it's got to be a horizontal line, and it's got to have a same length. So B3 we can draw from point B and call that end point of that 200-inch line as 3. Right, because this one B3 has, actually let me copy all of that, because we determined that each of these top chords should have the same exact internal force, which is 20,000 pounds. So the second horizontal on B3 on the force diagram should also read as a horizontal line with the length 200 inches. So 3 you can determine to be here. And same thing actually for this, which is C5. And same thing for D6, E8, and F10. So I'm just gonna do this whole thing, and you should be able to draw five, 6, 8, and 10. So you should have 1, 3, 5, 6, 8, 10 lining up right next to A, B, C, D, E, and F. I can wait, or can I move forward, or should I wait, or are you guys okay? Okay, so if you are drawing, do you have something like this more or less? Well, not yet. Okay, so I guess I'll move forward. So now, right, another thing we know is these verticals are verticals unless we're designing it to be vertical, so we know they are vertical, right? So even though we don't really know what the lengths should be, we know them to be vertical, right? And so I can actually chop that member off right there. Kind of the same thing. So B3 we knew. So if I move to here, let's move to the second top point here, right? So now, I guess just for clarity, I'm gonna copy these zones 1, 2, 3, B, and A. Change the color maybe. So I'm kind of zooming into the top chord second point from the left, right? So A1 we know because we already mapped it. B3 is here, right? 3-2 is supposed to be some kind of diagonal. We don't even know the angle, but let's just assume, right? So from 3 you probably have some sort of a line, and 2 has to be somewhere here. That's what we are gonna assume. So I'm gonna call this. The thing is, currently we don't even know what the angle of this diagonal is supposed to be. It's some kind of a diagonal, and 2 is somewhere on that line. So really a lot of unknowns. But soon we don't really have to worry about that, but because we're gonna find out from this vertical line, which is 1, 2, we will learn that there should be a vertical line connecting from point 1 to point 2. So there's got to be a vertical line from point 1 on which point 2 lives. So from these two clues, we are actually forced to conclude that only possibility for where the point 2 is actually the same as point 3, because it's intersection between this vertical and this unknown diagonal that starts from point 3. So we can delete all that and determine that point 3 is in fact also point 2. So this guy is actually point 2 and point 3. And then so force in the member 1, 2 is between, is determined by that line, right? And then we have 1A again, which is this guy. So we kind of used everything we can to determine. Basically, we got all the information that we can from that node. So we are kind of done with that. So I guess we could move down to this spot. Let's delete these. Now, next line here, we know it's gonna connect to here, but we really don't know the angle of this thing yet. So I'm just gonna draw it at some sort of a ridiculous angle here. And then I'm gonna copy again these zone names, 1G, 2, and actually this should stop, the vertical member should stop there, so it's really 1, 2, and G. So we're gonna analyze this. 1, 2, well, G1 we already know because we got this, and that's how we determine the angle, right? 1, 2 we already know from the previous node, and so the only new thing that we find here is this diagonal should be called 2G, and the angle you should be able to determine by connecting point G and point 2 in the fourth diagram. So actually this diagonal member shouldn't be, we drew it purposefully wrong, but instead of this, it should have had an angle like that. So I'm gonna delete this, right? So that's basically, and we're gonna cut it here too, so that we can design the next one. But so we got this far, basically 1, 2, and these two diagonals. So this determines this, right? So we keep moving to the next node, right? 15 minutes, so it should be good. But by now you should kind of see the pattern, or actually after this you definitely see the pattern. But let's do that. Oh, by the way, that 2, 3 is 0, but that diagonal code, because we are designing it to be here, it's there. Anyway, so if we go to the next node, right, it's BC, we already have that. C5, we already located it. And 5, 4, it's kind of the same thing now. We don't know the angle, right? But it's some kind of a diagonal. And 4 would be on this line, but we don't know, so I'm gonna put a question mark. Then again, we go back to this vertical, which is 4, 3. So that tells us there's gotta be a vertical line from 3 on which the point 4 lives. So again, point 4 is on this vertical and that unknown diagonal. So the only choice for that would be, for point 4 to be identical as point 5. So that's basically what's gonna happen here. So you probably already realized, actually we're done with these two, right? So actually from there you should be able to tell actually 6 and 7 is identical, because you're kind of following the pattern, right? So it's safe to assume that 8, 9 is same too. So you end up with 1, 2, 3 and 0.45, 0.67, 0.89 and 0.10. Let's just continue a little more down to that lower point. If you move this analytical node down there, again we want to determine the angle. I'm going to draw it wrong. Maybe turn that red or something. Then yeah, let's copy the zones, which is 3, 2, G, and 4. So really we already know 2, 3 is 0, 3, 4 is vertical, we already mapped it. G2 we already mapped that, so the only thing we don't know here is 4G, which should be determined by the line that connects point 4 and point G on the force diagram. So the bottom chord here should take the same angle as the force diagram, therefore that red assumption is wrong. And I'm going to trim that vertical there, and that diagonal chord should also connect from corner to corner. So basically we are now, you can keep going, but because it's symmetrical, right, you can pretty much assume this to be symmetrical, right? And what happens also is your diagram should also be symmetrical. So I can mirror this from point G. And so each of these lines are determining the angle of each of the bottom chord. I guess to do so I think you see a correspondence between these lines. The color didn't really help, but this is parallel to this one. So each of these are determining the angle of the bottom chord. And another finding is also all of these verticals 1, 2, 3, 4, 5, 6 and 7, 8, 9, 10, that's determined by these. So 1, 2 is 60, so therefore what is that, 6,000, 6,000, 6,000, 6,000. So the internal force, and actually if you want to determine whether it's tension or compression, you can, for example, look at that, but it's probably compression, right? Like you can look at this point, it's 2 1. 2 1 is upward arrow, so the internal force at this point is pointing up, so it's in compression. So all of these vertical ones are in compression. And the interesting thing is it's exactly the same magnitude as the applied force. So all of these vertical force is pretty much going down directly to the bottom cone. And another thing is that all of these diagonal members, 2, 3, 4, 5, 6, 7, 8, 9, if you try to determine the dimension, for example, of line 2, 3, point 2 and point 3 is identical, so if you drew a line, it's going to be a length 0. So that diagonal member between 2 and 3 has a 0 force. 4, 5, same thing, it's a 0 force. 6, 7, 8, 9, all of these are 0 force. So in other words, you can actually, if you removed it, it wouldn't do any harm, because that's kind of all that's happening. And the reason why this kind of efficiency is possible is the bottom part is pretty much what is called funicular curve, right? It's basically same thing as this hanging cable, right? So it's kind of like this truss is basically this compressive stick with constant force in its entire length, and this tension cable at the bottom, and then compression struts in between, right? So it's kind of like how do you call this thing? The bow. It's like you take a bow and you put bunch of struts in between and fixing the bow at that point. Let's just so we know that's gotta be all tension. To determine the magnitude, you can actually get the lengths again, right? So, and they vary from 250 to so the internal force here, in this case, it's like 225,000. Tension, and I'm just gonna use that 21932. That's here, and next one is 20224. And all of the diagonals are 0. And I can mirror all of that. So that's pretty much the truss we got, and you can in fact remove this and call that your roof truss. And I don't know if I post this PDF. I will post this PDF at some point, or maybe now or later. So we're gonna do a series of another set of these efficient trusses, but let's see. I wanted to show this bridge, not this bridge, but I'll show you next time. But you will see a structure like this a lot. Like some of the bridge might have this shape, or like this example that I would share with you. In this case, it's a like this one is a compressive arch at the bottom and these struts and the the bridge at the top. But when you see a truss, maybe not a truss, but this kind of structure which has either a arch or hanging cable form at the top and the bottom. So this is probably this is just a hanging cable example, but you would see these structures with one side being flat and another side being arch or hanging cable. Structure like that is very likely that it won't have a diagonal member because of exactly what we just demonstrated, which is right, because all of these force is all the applied force is being transferred to the bottom chord in this case, and bottom chord is doing all the job by taking this geometrically and structurally efficient form. Therefore, you don't need any of these diagonals. So you might see a bridge like this, or you might also see something like, on like 5 freeway, you probably, like whenever I commute from, like if you're going from downtown to Burbank, like some of these old concrete bridge above the freeway has this type of geometry, which is, in this case, it's a flip of the hanging cable, right? So that's a compressive arch, and all the loads are basically being transferred as a point load, and so therefore no diagonals needed. So, but I guess just pointing out that if you see a combination of this flat and arch or cable shape, it's very likely that you only have these verticals in between, and then probably the force in that flat portion is constant, and so on and so forth. So I guess the question for the homework was asking for the depths of this thing, which I only share with you for 2 seconds. But now you're able to do the homework, and I think we'll do a few other examples of how to design these efficient trusses. But another thing is we don't have a class on 19th, President's Day. So we don't have a class, and so the next class is February 21st, where we will talk about a couple of other efficient trusses, and then I think hopefully the week of 226 we're gonna move on to lateral forces. And I may or may not, if I was good, I may post a video explaining something, and that if I did that, your homework is basically this one, this week 5 homework. And if I did post a video, I will post it here and put an announcement. You should watch that video before the class next week, so that would kind of substitute the missing date. And so see you next week.